Research from Tel Aviv University, Harvard, and Ben-Gurion University defines a distinct class of malware targeting LLM applications, which is termed promptware. This new class of malware increasingly involves multi-step sequences that mirror traditional malware campaigns, moving the analysis beyond the simple framing of prompt injection. To analyze these threats, the researchers introduce a 5-stage kill chain model. It adapts the structure of the traditional cyber kill chain specifically for LLM-based systems. The stages are initial access, privilege escalation, persistence, lateral movement, and actions on objective. The kill chain begins, logically, with initial access. This is the phase where an adversary's malicious instructions enter the context window of an LLM application. This stage exploits a fundamental architectural property of large language models, their inability to reliably distinguish between trusted instructions and untrusted data. To the model, all input is processed as a single unified sequence of tokens. Access is gained through 2 primary methods. First is direct prompt injection, where the attacker is the user and directly crafts input to bypass guardrails. Second is indirect prompt injection, where an attacker embeds instructions in external content like web pages or emails that the LLM later retrieves and processes. Following initial access, the second stage is privilege escalation. Here, jailbreaking techniques are used to cause an LLM to bypass its own safety alignment and perform actions it was specifically designed to refuse. It is important to treat prompt injection and jailbreaking as distinct stages. Injection is what achieves the initial access to the context window. Jailbreaking, on the other hand, is what achieves privilege escalation within that context by subverting the model's own safety filters. Jailbreaking techniques have evolved well beyond simple instruction overrides. Documented methods now include persona-based attacks, role-playing, obfuscated attacks using things like ASCII art, universal adversarial suffixes, and even delayed tool invocation, all designed to get around application layer filters. The third stage is persistence. This allows malicious instructions to survive beyond a single user interaction, establishing an attacker's continued presence on the system. Promptware achieves persistence by exploiting the data stores that LLM applications depend on, including retrieval-augmented generation databases and agent memory modules. These persistence mechanisms fall into 2 categories. First is retrieval-dependent, where the payload lies dormant in a data store and executes only when retrieved. Then there's retrieval-independent, where the payload is stored in active agent memory and executes on every single subsequent interaction. The most advanced form of persistence establishes a command and control, or C2 channel. In this scenario, a persistent instruction forces the agent to fetch and execute new commands from an attacker-controlled source. This allows for dynamic payload updates and remote control of the compromised agent. The fourth stage in the kill chain is lateral movement. This is where the promptware propagates from the initial point of compromise to other applications, users, or systems. This phase exploits the inherent connectivity of LLM ecosystems. It leverages shared data stores, messaging channels between different agents, and the broad permissions often granted to these AI agents. Observed propagation mechanisms are varied. They include self-replication in generated content, the exploitation of unified OS-level permissions, and the traversal of data pipelines between integrated enterprise systems. The agent flare attack is a clear example of pipeline-based movement. It works by exploiting the implicit trust between integrated systems. The attack begins when a poisoned support ticket containing the malicious payload is submitted to an enterprise system like Zendesk. That ticket then flows through the data pipeline from Zendesk to Jira, where it persists. The payload remains dormant until a developer uses an AI-powered editor, in this case Cursor, to retrieve and summarize the ticket. That action pulls the payload into the editor's context window. Once inside the context window, the payload activates. It instructs the Cursor editor to abuse its own tool permissions, search for sensitive credentials in the local environment, and exfiltrate them to an attacker-controlled domain. The final phase of the kill chain is actions on objective. This is where the attacker's ultimate goal is finally achieved. The potential impact is determined by the specific permissions, the available tools, and the overall level of automation of the compromised LLM application. Documented malicious outcomes have escalated significantly. They include data exfiltration from email assistants, phishing campaigns, physical impacts through controlling IoT devices, financial theft via unauthorized crypto transfers, and even remote code execution by exploiting shell access in AI-powered IDs. Several recent studies have demonstrated the complete end-to-end kill chain. Specific attacks like invitation is all you need, here comes the AI worm, and agent flare have been successfully mapped to each of these 5 stages. The paper concludes that this kill chain framework offers 3 main contributions. First, it provides analytical clarity for threat modeling that goes beyond single-stage prompt injection. Second, it enables systematic risk assessment across all 5 stages. And third, it establishes a common vocabulary to help bridge the AI safety and cybersecurity communities.